Welcome to Part 2, Section 3 of the Searching and Sorting Contact Manager project. So today's lesson, we're going to begin our sorting algorithms tour. And we're going to begin with something we call a selection sort. So before we begin, we're going to look at a brief animation that demonstrates how a selection sort actually works. There will be a link to this on the website so you can view this animation yourself, but for right now we'll just use the video. Here we go. We're going to go to the selection sort animation. Okay, so in this case we're going to be sorting a series of numbers that start off mixed up. Now in this version of the selection sort, it's going to do this. Each pass of the outer loop is going to look for the biggest value it can find and put that at the end of the list, moving backwards through the list, putting the next highest value in front of the previous highest value until all the elements are sorted. So let's go ahead and we start with 75 is our current value that it thinks is the biggest value it can find in this list. It proceeds to look at each element. 75 is still the biggest because it's comparing 75 to 34. It continues to be the biggest because 75 is bigger than 4, but it is not bigger than 91. So now 91 is the new largest value it's found so far. It continues on until it finds a new biggest value. 99 becomes the new biggest value, and it gets to the last element in the list and says, well, if I compare 38 and 99, which of these values is bigger? 99, so 99 belongs in the 38 spot here, the last location in the array, so it's going to swap 38 with 99. And then it's going to pick up looking for the next biggest number, starting with the first element in the list, which is 75, comparing that to each value. When it gets to 88, oh no, we found 91. It says 91 and 88. Well, 91 is bigger than 88, so it's going to put 91 in the 98 slot and move 88 over here to where 91 is currently residing. And then it's going to start over, this time looking for the next biggest number, each time starting with the first element. And if we continue this process, 88 gets put in the spot currently taken by 63. And as you should be able to see by now, each time it's selecting the next highest value, thus the term selection sort, and putting it into the next available slot at the end of the list. Now the version of this algorithm that we're going to write today is going to be sorting contacts, and we're going to go about it by actually doing the opposite. We're going to start by putting things at the beginning of the list. Okay, and now we've got a fully sorted list. So let's go ahead and look at how we put this into code. So we're going to need to begin by creating a new class that we're going to call our sort runner, because we're going to put 3 sort methods in here over the next few days. This is just the first run that we're going to have. Oops, it didn't take my folder there. Let's try that again. New class, sort runner, public static void main, click finish. Now for this one, I'm going to use some really long variable names because I find that when we're writing these, it really helps if you're very clear on what each thing is actually doing. So the very first thing we have to do is have a list of contacts to sort. So we're going to say list contact, which creates my list that I can populate somehow. I'm going to make it a list of people, and I'm going to use that contact library that I created and provided for you to make contacts which are going to be in the order. Oopsie, we need contact.lib contact lib dot, and we want an unsorted list of contacts, and we're going to start with a very small list to sort. Okay. Now, we have this red line here because we haven't imported a couple of very critical classes. We need to import java.util.list. Okay, now we can continue on. So the first thing that we're going to want to do is see our list of contacts, because we're going to want to see it both before and after we sort it. So we need to write a print contact name list. But rather than go through that process again, we're going to skip over to our search runner, and we're going to go ahead and we're going to grab that bit of code, switch back here, and paste it in so that we can use that. Okay. Now, our next thing is going to be, we're going to go ahead and print our contacts with the title contacts, and we're going to print people. Now we want to take a moment just to verify that our code is working, so we go ahead and run it and see if we get a list of 5 contacts, and we did. Oh, that's funny, we changed this to a tab. Let's go ahead and just make that a space. There we go. Okay, so we've got our contacts here, and now what we want to do, and we can see that they're not in alphabetical order, so the next thing that we want to do is actually write some code that will go ahead and sort these. Okay, so we're going to make a public static method. Now, normally when we're sorting, we wouldn't have to have any return value, but in our case, we're sorting and we want to know how efficient it is, and we're going to measure efficiency by how many iterations it takes to fully sort a list. So we're going to have it return an integer value that's going to represent the number of iterations used to complete this sort. The name of the sort is selection sort. We're going to take as an argument a list of contact, which we'll call contacts. Okay, and then because we're going to be keeping track of iterations, we'll go ahead and set that equal to 0, and we can go ahead and fill in the final line of our code here, which is going to be to return iterations. Now you might be asking, well, don't I need to, whoops, I returned twice there for some reason. Don't I need to return my contact list? But remember, I can shuffle elements within my contact list, and it will be changing people, because what I have is I have 2 different references to the same list. So if I alter the list, I'm really altering this same list here in people. Okay, so let's get back to writing our code. So the first thing that we need to do, if we go back and look at this, the first thing that we saw was that our outer loop looped through each element, starting with the first, going to the last, or at least close to the last. So what we can say is that we have to have a loop that looks at each element, which represents the next index that we want to fill. And we start with the first index element, and then each time that index to fill is going to be less than contacts.size minus 1. And then finally, next index to fill is going to go up by 1 each time. By the way, I'm going to go ahead and close this down because we don't need it. Give us some more room to type here. Now, what is all of this doing? Well, the outer loop is going to iterate from the first to the second to last element, so we can find the next, let's go ahead and put this in quotes, next lowest element. Now it's important to understand, why are we skipping the last element? Well, if I sort all of the elements into order except the last element, because I'm putting the lowest element first, when I get to the end of the list, the last element must be the highest element. It must be the biggest one. By elimination, I've already gotten rid of all of the other lowest elements, so the last one has to be the biggest one. And it's already in the last position, so I can sort of skip it. Okay? So that's that step. Well, what are we going to do next? Well, we're going to start by assuming that the index of the smallest is equal to the next index to fill. What does that mean? Well, that means that we assume the next index to fill already has the smallest value. Because what we're effectively going to do next is a really common algorithm in computer science. We're going to find a minimum value. So when you're thinking about the next series of steps, think to yourself, what would I do if all I wanted to do was find a minimum value? Okay, so how would I find a minimum value? Well, I need a for loop that's going to say, I'm going to have a possible smallest index, which is going to start at the next index to fill plus 1. Why am I skipping past the next index to fill? Well, if I assume that next index to fill is the smallest, then the next one that I have to compare it to is the one that comes right after it, which is next index to fill plus 1. Okay, and then I'm going to say if possible index, possible smallest index is less than contacts.size, then I'm going to say the possible smallest index gets added, gets 1 each time. Now this time I'm going up to the last element in the list, because as I'm looking for the smallest element, I can't afford to skip that last element because it could still be the smallest at this point. Okay, so what's next? Well, let's describe what we're doing here. We're looping through the remaining elements to see if any are smaller than index of smallest. Okay, so how do we do that? Well, we have to take one little divergent step here, and we have to say, since this is the inner loop, let's go ahead and update our iteration counter here. So what's happening here is we're going to say iterations gets increased by 1. So each time this outer loop executes, this inner loop has to execute at least once. And therefore, we're going to add 1 to iteration counter here, and in that way, iterations will be equal to the total number of times that this algorithm has repeated itself. Okay? And now we're on to the next item, which is to retrieve the last name first for both the current recorded smallest and the possible smallest. Well, how do I do that for an array list? Whoops, that's not how you spell retrieve, is it? There we go. How do I do that for an array list? Well, in this case, I'm going to be comparing 2 strings. So I'm going to create a string, and I'm going to say the current smallest is equal to my contacts.get. And then what index do I want to get? I want to get the index of the smallest. That's the smallest one in my current array. Oh, and then I want to get last name first. Next, I want to take the string that represents the, let's see, this is the possible new smallest is going to be equal to contacts.get. And this time I want the possible smallest index. and I want from that the last name first so I can compare them. Okay. Now, when I'm finding a minimum value, I want to compare my current smallest to my possible new smallest to see if I have a new smallest. So I do that by saying, in the case of strings, I'm going to compare current smallest to my possible smallest and see if that result is greater than 0. With compare to, that means that would tell me that this possible new smallest is actually less than my current smallest. What does less than mean in this case? It means that I've compared them lexicographically, and possible new smallest comes first alphabetically. So what I'm doing is I'm testing to see if possible new smallest comes first lexicographically. That's a tough one to spell. And if it does, then it represents my new minimum or smallest value. And so I'm going to say the index of the smallest is equal to the possible smallest index. Okay? And now I'm moving on. Oh, we can put a little comment in here to make it clear what we're doing. We found a new smallest value. Okay. All right, what are we going to do next? Well, at this point, we can wait until this outer loop ends. And now we need to do some fancy swapping of elements. So now we swap the smallest value we could find into the next index to fill slot. Well, let's just leave it at that. Next index to fill. So how do we do that? Well, with an array list, it can be a little tricky, so we got to do it one step at a time. I'm going to create a contact that's going to represent my smallest contact, and I'm going to get it from the list. You can see here why using really long descriptive variable names makes it easier to write this code, and hopefully it makes the code easier to read as well. So now I've got my contact that represents my smallest contact. So what do I want to do next? I want to have my contact that is my contact that is being swapped is equal to contacts dot set index of next to fill. And what am I going to put in that position? I'm going to put my smallest contact. Now, this line of code can be very tricky. It's important to remember that when I set a value in an array list, what I get back as a return value is the element that was at that location. So what I've done is I've said, I'm going to put the smallest contact at the next index to fill location, and I'm going to get from that process the contact that was there. And we're calling that the contact being swapped. So now the last thing to do is I have to say contacts.set, and this is going to be the index of the smallest, and now I'm going to put the contact being swapped in that slot. So what I've done now is I've used set again. This time the location where I'm putting the object is the index of the smallest object. And what am I putting there? I'm putting the object that used to be in that slot that we just needed to fill, the next index to fill location. Okay. And when I'm done, all I have to do is return iterations. And that is the complete code for a selection sort using an array list. All right, so let's see it. Let's see the results of this. So we're going to go up here and we're going to say int iterations equals selection sort people. And then we're going to print contact name list after sorting. And let's print out print contacts. I'm sorry, it's just print contacts. Got a little carried away there. Print contacts. And then at the end of the list, let's also print how many iterations it took. So let's do a system.out.println, and we're going to say list sorted in iterations. Okay. All right, let's show our console here. And we're going to go ahead and expand its size a little bit so that we have room. And click in our window here, run our code, and I guess I didn't make it quite big enough. So here's my original contact list. Redding, Newbie, Bowden, Fu, and then Wong. Here's my sorted list. Bowden, then Fu, then Newbie, then Redding, then Wong. And the list is sorted in 10 iterations. So the next question is, well, what happens if I increase the number of items to be sorted? So let's make it 10, and let's watch what happens. So it took 10 iterations to sort 5 elements. How many iterations will it take to sort 10? You might guess that, oh, well, it should take about twice as many. Whoa, what happened? It took 45 iterations. That is considerably more than twice as many. So what we want to do next is we want to graph and see what it actually looks like as we sort more and more items in our list. But we're going to use large enough numbers that it's not going to be tenable to actually print our list. So we're going to comment out those 2 lines. And then we're going to go ahead and we're going to start with a number like 500. And let's run it. And look at that. It took 124,750 iterations to sort 500 elements. That is a lot. You know what? We can put in let's go ahead and put in our print context for our after sorting, and let's go ahead and run that. Just to confirm. Now notice one other little detail. Due to a little error in the contact lib, notice that Hibbit here didn't capitalize her name, and lexicographically lowercase letters fall after uppercase letters, and therefore she got sorted to the end of the list. That's not really a problem with our sort algorithm, that's a problem with the data. And that is an error that is commonly called garbage in, garbage out. Okay, so here we've got our list. Now what we're going to do next is start in on the homework assignment. To complete the homework assignment, you're going to need to go to the website and download the sorting algorithm worksheet homework assignment, which looks like this. And notice that the first thing you're going to do is sort 500 elements. So what is that going to look like? Well, I've gone ahead and let's see, we're going to hide Google Chrome here, and I've set this up so that I can enter that. How many iterations did it take? It took 124,750 iterations. Let's go ahead and make that 1,000 and see what happens. You know what? I caught myself making an error here. Notice it says for data sorted in reverse order, but that's not what I have here. I have data in unsorted, so let's fix that. Let's make this dot descending. That's reverse order, and let's run it and see if our answer changes. Whoa, look at that. Our answer changed a lot. So data that's sorted in reverse order is our worst case scenario. It means that every single element has to be changed. So we've got 499,500. 499,500. Oh no, that was for 1,000. My mistake. Hold on. Nope. Let's go back and change that to 500 and see if that actually changed. Maybe I was wrong. Nope, I was wrong. 124,750. Sorry about that, folks. This one should be right over here in the 1,000 box. And then what we should have here is our 124,750. What's important to notice here is that this number more than doubled. So what we're going to want to do is continue filling in the rest of these here, and then we're going to graph them down here on the next page. We're going to graph the worst case. Now, we're also going to want to run this same set of tests here by running these tests again, but where the data is already sorted, to see if it makes any difference in the way our algorithm runs. So we're going to do order ascending. So if I run this in ascending order, what am I going to get? Look at that. I got the same exact number. And if I run it for 1,000, what am I going to get? 499,500. So at this point, I can conclude that data in the optimal order is actually exactly the same as data that is in reverse order. This algorithm does not get any more efficient when the data is actually sorted for me. That makes it not a particularly good algorithm if I know that my data is already sorted. And then finally, I'm going to want to do that same last series of tests here for order unsorted and see if those numbers change. Run it again. And I see that the numbers didn't change. Let's double check that by doing 1,000 as well. And sure enough, those numbers didn't change, so I can effectively just copy these numbers down here. And you can see that I'm on my way to filling out my chart here. So what I need to do to complete the homework assignment for the selection sort is continue graphing for the worst case, which is reverse order, the optimal case, which is ascending order, and then unsorted, which is the equivalent of random order, for each of these numbers of elements, and graph the worst case on this chart here. And then I'm going to attempt to describe what it looks like in terms of an equation for the best case, worst case, and average case for each of my versions here. And the average case is the random order. What does the equation look like? Well, that should be easy for this one because all the equations are going to be the same. So I'm going to, once I have graphed all of that information, I'm going to try and figure out what the shape of that curve looks like and see if I can write an equation that describes that graph. What's the relationship between the number of elements and the number of iterations it takes to sort that list? And that is the assignment for the day.